So good morning, everyone. Welcome to this exciting session on digital twins, where we explore how this cutting-edge technology is transforming and reshaping the way we better understand and interact with the physical world. So I welcome to the stage Jules-Edouard Denis. He's a data scientist and project manager in Airbus Defence and Space, and involved in many digital twin initiatives. So we are excited to hear your speech.
Thank you. So hi everyone, I'm Jules-Edouard Denis and I'm going to present you my DIGITWIX project. So let's start with some context. So here is a telemetry coming from a TELECOM satellite. And you can see that there is a big difference between the margin of security, here in red, and the true level of behavior of the satellite. And when we investigate a bit, we can see that this is mainly due to bad estimations on some parameters. For instance, the bad estimation of the aging, on the dissipation, and so on. And all these effects are stacking each other, raising a large amount of margin. So if I recap, today, we are using satellite simulators based on hypothesis, conservative hypothesis, and it traces static and conservative scenarios. So it is not possible to optimize your payload efficiently. And what we are proposing tomorrow is to aggregate the telemetries, automatically treat it, and then automatically correlate the simulators, permitting to have representative what-if scenario tools. So that's the scope of my DIGITWIX project. And one of the big challenges this kind of project is to produce the model corrector, which is based on machine learning. This model corrector will fetch the telemetry, compare it to the satellite simulator observations, predictions, and then calibrate the simulator in consequence. So there is 3 steps to do that. First one, we have to modify the simulator. Step 1. Step 2, we have to build this technical brick consisting the model correction. We can base it, for instance, on machine learning algorithm. And finally, we have to integrate all these technical brick in the ecosystem of the industrials. That's why we put in place a consortium with Airbus Defence and Space and Thales Alenia Space. And we also include the French Institute of Technology Saint-Exupéry to do that. So I will then present you what are the main results of the DIGITWIX project, which is still ongoing, on all the 3 elements. So let's start with modeling. We wanted to start from toy cases to build the methodology. That's why we put in place a prototype of thermal power model based on Open Modelica framework. So you can see here models of increasing complexity. And here is the main results. On the left, you have the parameters which are estimated by the Open Modelica models, and on the right, it is the corresponding real telemetry observed on a true satellite. So it is quite close, in fact. So, okay, we have put in place our toy cases, which are quite representative of real behavior of a satellite. Then let's synchronize it. Let's correct it with a model corrector. To do that, we choose a machine learning approach because there is a lot of advantage. To train the machine learning approach, we have to generate a lot of data. So how to do that? We generate a lot of random parameters, random profile, for instance, aging profile, dissipation profile, and so on. We put it on a simulator and we observe the corresponding features, for instance, the temperature here. And then we train our AI model corrector to do the inverse process. That's why it's called an inverse model. From the observations, try to estimate the profile of aging, the profile of dissipations, and so on. Okay, this is pretty, but there is still some, of course, technical challenge to do that. First one is the computing time. We have to manage the computing time because we have to generate a lot of simulations. Second big challenge is the generalization capability because, of course, it is trained on simulated elements, and if the model corrector sees real temperatures coming from a real satellite, it shall behave well, in fact. Okay. So the main advantage of this approach is that we train one single time the model corrector at the beginning of the mission, and after that, it is capable to propose new profiles. You can call it each hour if you want. It is costless. Okay, this slide, I will be very quick. You have some details on the article. So, in fact, we run some scenario, and we compare our model corrector machine learning based with other approach, for instance, optimization loops, which are very, very costly, but also very precise. And what we prove on these toy cases is that we have quasi the same results, but the model is, the AI approach has a cost which is weaker. So, of course, it is still a work in progress, and we have to test it on more precise simulators. Okay, then, how to integrate all these pretty elements on a real infrastructure? What we imagine is a parallelization approach. So, put instances of simulators inside Dockers, put them in parallel, and then dialogate with each of these Dockers via an API. And the advantage of the consortium is that there is Airbus DS and TAS in the consortium, so we can build a common API, a common approach, permitting to be compliant with these two industries. Okay. So I have presented a lot of things. I want now to show you what is the long-term vision about digital twin, because of course this is very pretty to put in place AI, a machine learning approach permitting to correlate models and so on, but is it realistic, and how difficult it is to deploy it, to test it, to validate it on an industrial environment? To solve this question, we put in place digital twin factory approach. And here is a sketch of what can be this digital twin factory. So it is composed by 3 elements. The first one on the left is a big component library, a model database permitting to store a lot of models. Then you can easily pick the model you want inside it, permitting to assemble your own simulator and run simulations inside a simulation platform. And after that, we have to communalize some analytics tools, anomaly detection, what-if scenario optimization, synchronization, and so on. So the advantage of this end-to-end approach is that it tackles all the life cycle of a satellite from the design until the operation. And also it permits some reuse between the programs. Okay, so just to recap and conclude, today we are developing technical bricks to put in place a spacecraft digital twin, This is, of course, still a work in progress. There is a lot of work to do. Next step is to test and deploy it on real simulators with real satellite data. One of the key things to bring back from this presentation is the two last sentences, the open questions. First, we have to think about a standardization approach, and I think this is the role of agencies today to impulse it. And second, we have to think about how to qualify this kind of system because it is based on AI approach, and we have to be sure that we know that it will be robust enough for operation. And this have to be solved by all the space ecosystem. So thank you, everyone. If you have any questions, do not hesitate.
Thank you very much, Jules, for the interesting talk. Any questions from the audience to Jules? If there are no questions, then I have one or two questions to you, Jules. One question is, when do you think, what is roughly the timeline when this could be operationally used? And the second question would be, could you also predict failures which may happen on board of the spacecraft in advance so that you see a degradation of an instrument over time, and could you then see that most likely something could happen and prevent it?
Okay. About anomalies, this kind of tool, of course, will not permit you to anticipate the big failures, but it will permit to anticipate the trends. For instance, the aging trends, if a satellite is aging faster than expected, for instance. That's why it's very interesting, because the today's tools are, we cannot do that with the today's tools. Sorry, but what was the first question?
And the first question was, when do you think that can be operationally used, the time horizon that you have in mind?
Okay. I have prepared a slide to do that, to answer that. Okay, so in fact, there is a diversity of digital twin. Today, we can display information on your satellite, but it is not sufficient to run scenario. And in fact, today, we have at the stage of a predictive twin. We are capable to predict trends. What I'm proposing today, it is quite medium term, is to do the next step, the comprehensive twin, permitting to run scenarios. And the step after, it is much more long term, so perhaps 10 years, will permit to optimize this scenario automatically.
Okay. Thank you very much, Jules.
Yeah, good morning also from my side. We move now from digital twin of a satellite to the digital twin of the Earth. The next talk will focus on the Destination Earth data lake and will be given by Daniele. She's Destination Earth use case and partnerships representative at EUMETSAT, and next to that she's also focusing on the definition and evolution of the data portfolio. I think that's two very important thematics, and yeah, Daniele, the floor is yours.
Thank you very much for the introduction, and good morning to everyone. So today I will present you the Destination Earth data lake and how it unlocks the potential to work with big Earth data processing. So I will explain you first what is DESTINE, but then I will focus my presentation on the lake, one of the components. And I hope by the end of my presentation we'll have more info about what's other services provided and how it works behind. Okay, so first of all, what is Destination Earth? It's a European Commission initiative which consists to deploy a highly accurate digital model of the Earth together with the ecosystem to use the data coming from the model and to access to those data, to create new information out of it. So for this initiative, the Commission entrusted 3 entities to deploy 3 components. So which are the components? So there is the core service platform developed by ESA, which is the entry point for user. Let's say it's the web portal, but not only, it also provides advanced services. So the user will enter to the DESTINE world via the core platform. Then, of course, within the system, there are digital twins, 2 of them, developed by IMMERSIVE. So the first digital twin is about climate change adaptation, and the second one is about extreme events. So this is a blue bubble, what is developed by IMMERSIVE. And then there is a EUMETSAT data lake, for the Destination Earth data lake developed by EUMETSAT, which consists to provide access to the digital twin data, also to other data sets, and also, as well together with big data processing services. So this is how it works together. Now, from where EUMETSAT starts and what is, from where we come from. So from a long time now, EUMETSAT has been an expertise building data services and on data management then, and also distributed cloud solutions to respond to their user requirements and user needs. I can cite 2 of them. So there is recently the EUMETSAT, built since quite a long time now, but it's the EUMETSAT data lake. It's an internal data lake to provide access to EUMETSAT data. In terms of the second initiative I can speak about, it's a European Weather Cloud, which is developed jointly with IMMERSIVE, in which facilitate distributed processing, so developing a cloud solution. Also, in terms of federation, since quite a time now, we are involved in federation project, and it's aligned, of course, with the big data strategy of the organization. So basically, we choose a synergy approach to build the Destination Earth data lake. So you will recognize on which pillar we base the Destination Earth data lake: data federation, of course, access to digital twin outputs, the new data coming out of the twins, and to support user with distributed processing and additional data sets. Yeah. So here you see a lot of text, and there is the onion diagram. You can look at the text when you will have access to the material, but I will focus on the onion only for you to explain the concept. So there are 3 pillars, and behind that there is 3 services exposed to user via the Destination Earth data lake. First of all, there is a discovery of services, big data processing services and data. There is a data access, so a possibility to access digital twin data, but not only. And the big data processing, which is to provide tools for users to work with this amount of data. So this is a central keyword in this onion diagram. If you go 1 layer after, why we provide, how we provide that in an efficient way, we provide the capabilities to work in proximity to the data. We talk about it very often this week, to bring really the user where are the data, to facilitate this, the access to the data and to work in an efficient way. So for this purpose, the infrastructure of the data lake is distributed over different places, close to the different data stores, but actually data fortress, we mentioned it before. So we provide the infrastructure is distributed close to the digital twin data. The digital twin data developed by IMMERSIVE are computed on HPC, and so there are some infrastructure from the Destination Earth data lake really physically close to the HPC, and the service deployed there. But not only, also there are fresh data pools where there are infrastructure close to them. For example, close to the Cloudflare fresh data pools, very soon close to EUMETSAT data as well. So the idea is to provide, in a distributed way, access to many data sets, the digital twin. On the right side, this is the blue block, and on the left side is to provide access to many data spaces, and thus many providers, many data stores. So I will now dive a bit into the architecture, but this is what you have to keep, keep in mind on this slide, it's again the distributed architecture. So there is orange blocks, which are the data lake blocks. And on them, you have the deployment of services. And all of them, all services, access to data, big data processing. I will explain later on what it consists about, those big data processing services, are deployed all over the places. Yes, and those are then exposed to DESP. I will insist also on the bridges. So this is the 2 blocks on the top, what we call data bridge, and where so which are close to HPC. We call that a reference architecture. It's a bit jointly designed with ECMWF to find like a reference architecture to be reusable to adapt, to connect to different digital twins in the future. And in blue, there is a data warehouse where the digital twin outputs from ECMWF are dropped and then make accessible for the users. Then I mentioned we provide access to many data sets, but on top of this access, we provide an harmonized data access layer in order to do an abstraction of the API behind. We try to expose everything in a uniform way. Of course, there is still the possibility to access directly to the buckets if the provider allows it. So I will continue because I don't have much time left. So we have to keep in mind access to digital twin output through the reference architecture of the bridge, distributed infrastructure, and federation of data in general. Sorry. What are the services? I recall here briefly, we discover either data or services. In terms of data, the last time I will say digital twin output, federated, but also user can generate data within the ecosystem of DESTINE and expose it later on to other users. And fresh data pool, it's when we have a cache of data, but we don't encourage that, but it is possible with the design choices. And in terms of big data processing, which were not very much mentioned yet, we identify 3 levels of big data processing services. There is what we call the ESLED service. It's in a way infrastructure as a service, so we can provide an environment for user to create some VM, request CPU or GPU as well, resources, Kubernetes cluster, etc. The second level, it's more for hosted applications, such as Jupyter Notebook, DASK usage. And my colleague right after will explain better and more in detail how it works. And then the last layer of service is the functions. So it's very high level. It's ready to use functions for user. Yeah. So you see there are different kind of.
Just to mention, there's only 1 minute left.
Yes. Okay. I finish very quickly, so I won't spend time because we'll have more information right after. But you see, it targets different expertise, user expertise. But what we have to keep in mind through this very nice animation, you can pick up those services as you wish, and you don't need to choose for one. It's really on demand. So if we go through a DEDL journey, Destinations Data Lake journey, you enter through the core platform, you can access to some data or to event services, and you can play with all of them. You compute your results, your model, etc., and you can bring it back to the core platform and either add it in your other services on the core platform or directly use the result. And you see how everything interacts together. In orange, there are the data spaces, and in green-blue, the digital twin. It's the consortium who develops that. It's Claude Ferro together with EODC and CS Group. And then you saw we have many data sets included, and we facilitate access to those. So we have defined a data portfolio, which is user-driven. Currently, it's what we provide, the twin data and data set from the 3 entities contributing mission. Also to Copernicus data, Eurostat, because we go way beyond Earth observation data. The idea is really to have in-situ data, IoT data, statistical data, everything.
I think we need to conclude
now. And now it's over. Yeah.
Okay.
Thank you very much. If you have any question, yeah.
So Daniele managed to use the time super efficiently, so thanks for that, and also thanks for the overview. We still have time for questions. Are there questions around? There's one in the behind left.
Thank you for the presentation. I have one question that is two, but I think it's simple. The first one is, we know that the Commission is also fostering the development of other digital twins. Is EUMETSAT still going to be the data lake for all the digital twins, so all the data is connected?
So we are exchanging with them. We are we know where everyone stands. There is a possibility in terms of infrastructure to do it because it's very scalable. We define, like you saw, reference design to build some bridge. So this is feasible. It's not in the scope of phase one, where we are now, but might happen in the future. Yes.
And the second, very quick, sorry. How is this connected, or is there any connection foreseen with the data spaces that are being also fostered in different domains like agriculture, transport, and so on? Is these spaces are going to be connected to the data lake of the digital twins?
Okay. Thanks again for the question. Yes, indeed. So we look at the data spaces defined by the European Commission, and we will provide, yes, some links to all of them. In an ideal world, of course, we have to start from somewhere, and so right now we choose what is needed for the use case we have procured in phase one, and which we identify very useful for the user in general. So, but that's the idea. Yes, thank you.
There's one other question, and I think then we need to conclude. Yes, please.
Thank you. Thank you for the nice presentation. So one of my first question is, will you provide a stack catalog or something that, for internal data that you have on data lake? And the second question is, like, do you accept the internet access from the processing server so that we can use for example, stack catalog inside, using the same thing, the data inside at the same time?
Okay, so first of all, to access to the destination's data lake, you need to enter via the core service platform. You need to get special rights because you saw we cannot, of course, accept everyone because we are limited in terms of resources. But to reply to the second question, so you answer through the core platform. If you are granted to get access to it, usually right now we are at the beginning, it's for use case owner. And then you can together access to the data and to the big data processing services.
Will you provide sort of catalog, like a stack catalog something of
and
the
so
data in data lake?
So there is definitely a stack catalog. We use stack standards. We are aligned with that. Our HDA is based on stack, so yes.
Thank you.
Good, then I don't see any further question. I think we can move ahead. Thanks again, Daniele, for your presentation.
So I asked to the stage Christoph Reimer. Christoph is the head of service development and operations at EUDC, and he will give the next talk.
Thank you, Michael. Thank you for having me today. Before I start, also kudos to my co-authors, so to the entire EUDC team doing the engineering part and the implementation of what I'm going to present today, and also to our colleagues at TOWIN supporting us in the prototyping and implementation of the use cases I will present later on. This talk is about multi-cloud processing with DASK, demonstrating the capabilities of Destination RS Data Lake. In the last days, we've heard a lot about how to break up data silos or new upcoming platforms and how to do federation. And this talk, I think, fits quite nicely into this discussion because it already demonstrates a concept on how to allow federation based on a technology layer like DASK. So why do we need multi-cloud processing or have to consider it at all? To find answers to these complex challenges of today, like climate change, We need to have access to a diverse set of data sets, and this data set is scattered, or data sets are scattered across the globe. So we're talking about satellite data, we're talking about model simulations, we're talking about statistical data, in situ data, etc. And accessing this data right now is can be quite challenging. Those are stored in so-called data spaces or are provided by digital twins, and those data sets are continuously updated. So if we now start a project, our first thing we do is basically we're going out there and see where can we collect all this data, and then we start to dump all this data into a central repository and do our work there. And as we have heard yesterday in the keynote speech by Ryan, those are like these data fortresses which are quite isolated from all the others and comes with a certain set of disadvantages. And one of the disadvantages I would like to mention is the factor costs, because what we're actually doing is data duplication. So we need additional storage to store the data. And furthermore, there's also costs related to the network traffic, because we always need to push the data between the different clouds, and this comes with ingress or egress costs. For me at least, one of the most underestimated factors in this equation is data management, because that's really a burden to keep the entire data archive. We want to have healthy and up to date to address the questions we have properly. So how can we do better? In general, high quality data also comes with an increase of data volumes, and we all want to make use of the best, highest resolution data sets out there. And we also know and have heard now that, for instance, all the digital twin outputs produced on a daily basis are like big data sets or large in size, and those are basically then available in addition to the already existing satellite data sets, which will also grow in future. So accessing these data sets via a single entry point will not be feasible any longer. So therefore, we need to go multi-cloud processing. So we need to move so-called computation to the data. How we are going to do this? So what we need to do is we need to bring the compute to the so-called data spaces or digital twins in terms of compute infrastructure, and this infrastructure should have been accompanied with a software layer providing a set of services or interface APIs to interact with the data. The advantage of this is that we reduce data transfer, so because we can only do the processing there and only transfer the data we really need over at the end. This also comes with a reduction in costs, because we don't need to provide all the storage, because we don't need to duplicate the data one by one, and also we reduce the network costs. And the data we want to access is always up to date, and the data management is almost zero for us, because all the management is done by the different data source providers. And this brings me directly to the destination Earth data lake, because this is exactly the approach concept followed in the architecture of the destination Earth data lake. So as you can see here, the destination Earth data lake, and as we have heard before by Daniela, is built of multiple geographically distributed cloud infrastructures, which are closely co-located with the Europe HPC systems, powering the digital twin engines. And by doing that, we get direct access to the outputs of these digital twins via the data warehouse co-located there. In the center, there's the so-called central site, which allows us, via the so-called harmonized data access, to federate additional data providers in and access those data in the same way as we do from the digital twins. Sorry. We've heard before about the big data processing services. So there are three of them. So there's the isolate service, the stack, and the hook service. I would like to now focus a little bit on the stack service offering there. So stack service is really targeting on a specific user group, so like non-IT or cloud experts. So we're focusing on community of scientific programmers, data analysts, or scientists, and support them in doing their work. This community mostly relies or makes heavily use of Python as their programming language of choice, and also makes use of the entire Pangeo software stack which is out there. Therefore, we decided to build all the services we have there around this ecosystem and support fully managed service built on top of Jupyter ecosystem. So we have the Jupyter Hub, Jupyter Lab, and also Jupyter Enterprise Gateway as service in there. And we also have the DASK ecosystem involved by specifically by the DASK Gateway and DASK Kubernetes as the compute backend. When we started the project, we asked ourselves what options are available actually to run DASK in the multi-cloud. So we did an investigation, and what you need to know first is we want to run DASK in a distributed way. So there's a DASK scheduler and the worker instances which need to communicate via a shared network, and this needs, in considering that would need a lot of effort to spawn a shared network across multiple clouds. So there is an approach like that presented by Karatosun, which basically creates a VPN across multiple cloud instances to share a network and join a cluster around those instances. Another approach we have investigated is that we spawn an entire Kubernetes cluster across multiple cloud infrastructures. This comes with a high complexity and even closes the federation just based on Kubernetes. And finally, we ended up in deciding to go for a solution using DASK Gateway as a deployment option. And we see the advantage in having a native API for DASK and allow scalability even outside of the entire data lake ecosystem. And this was implemented, or a proof of concept implemented by Augsburger et al. We took this concept a little bit further. We extended it by making use of a data discovery service provided by the Harmless Data Access. So as said before, it's a stack API. Within this metadata, you have information already about where the data is hosted. So we take this information, propagate this information through to our Python data model, which is basically X-array. There you can make use of annotations in the data array to say this data sits here or there, and then to connect or to route the computation to the different clusters. You have different cluster clients, and then based on that you can decide where to go and execute the computation there. I'm still running out of time, so therefore maybe I might skip this one. In order to support this, we have implemented a so-called stack client, which gives us the possibility to spin up DASK clusters on these multiple locations. Just if you would interact with one single cluster. It needs to be said that this is really tailored for the needs of the data lake project. What you see here is on the left, with just 3 lines of code, you can really just start your clusters and already start running some computations there. And on the right, we use this context managers to say where to do the computation at the end. We also had a use case implementation to prove that this concept works within the data lake. So we had 2 use cases with a high socio-economic impact selected together with TOBIN, which supported this implementation. So that's the Pakistan flood and the drought in Italy in 2022. And we run this what-if scenario. So we went back in time basically and run this what-if scenario, which is presented here. Yeah, I won't go into details because I'm already over the time. So maybe I jump over here. So what we have done there is we demonstrated that, for instance, an expert user comes to the data lake, starts his journey with a Jupyter notebook, implements the code needed to answer the questions of the policymakers, makes use of the DASK client library we've implemented, and based on the computations needed, based on the computations needed, the client proxies that towards the corresponding site. For instance, for the flood use case, we want to access GFM data from the global flood monitoring system, as well as the global human settlement layer. And this was all then done on the central side. And on the Lumi bridge to actually access or simulated outputs of the digital twins, we made use of Error 5 to access this at Lumi bridge at the end. Yeah, and in conclusion, I think that's a simple, powerful concept to be used to enable multi-cloud processing in such environments. There's no server proxy needed in front of it, so you can really do distributed computing in a quite flexible way. You can directly make use of the native DASK API, so there's no API facade in front of it. And we already have successfully demonstrated that this integration works also in the concept of the destination Earth data lake. Yeah, and with that, I want to close. Thank you.
Thank you, Christoph. Thank you very much, Christoph, for sharing those insights with us. We have a question for, one question from the audience. Vasilis, go ahead. We wait.
Hello, my name is Armağan Karatosun. I am one of the developers that you referred in your presentation about the VPN part of the DASK. And during that study, we also evaluated the gateway approach in line with our approach. And the main obstacle that we had was the fact that the need of sharing the information between during the computation. So DASK gateway was kind of assume that it was isolated in one environment and do the computation there. And if there is any need to load data from anywhere else, it just needs to transfer the data back to cache it. And this was creating some kind of a duplication, as you mentioned. I wondered if you did any changes on the source code to mitigate that? Oh.
No.
Okay, this was my question because it will be really interesting to see something like that.
No, we haven't done that until now, so we haven't had a look into that, but we are well aware of this problem still. But we're still, because of this flexibility we have, we still believe that we can do all the processing first to compress, let's say, the data, and then just transfer what is needed if we need to do the transfer.
Thank you.
Okay. Thank you very much. We can ask one more short question.
Hi. So my question is, so you mentioned that you have several gateways. If you can show me the, there was a Lumi gateway, and then there, not that one. I think you had a Lumi, and then you had some provider. So that means you have different HPC system behind your DASK gateway, right?
Yes.
Yeah. So like Lumi and the Leonard, and they have the same architecture? What about optimization?
So
it's the DASK image. The DASK image. How do you switch from that tell the user that you have to have ARM optimized and so on, right?
So the DASK gateway itself runs on the bridges. So they are not running on the HPC directly. So they are purely running on the data bridge, which is a cloud infrastructure. There's no direct connectivity right now to utilize the HPC resources. But to your second question, I guess, in terms of customization of what is deployed there, we fully support the providing your own image to be deployed in the cluster. So you can customize the entire environment you use for processing.
Thank you very much, Christoph. I think due to time, we have to go on to the next, and Christoph is available for questions outside.
Yeah, then. Then let's move on and continue the journey now from processing to visualization. So we have now talked on immersive visualization technologies in order to support digital twins within the concept of also the destination Earth. Nino, as director of CGI, Italy, will present us his activities within the digital twins in the context of Destination Earth, and he will especially focus on the ECMWF projects that have been implemented on top of that. The floor is yours.
Thanks very much, Chairman. Thanks very much for giving me this opportunity. So nowadays, we're all speaking about climate change adaptation. We're speaking about extreme events. Unfortunately, we witness the damages and the effects of all these things. And there are a lot of different stakeholders that are dealing with these complex phenomena. What we are trying to do is to try and find a common language which can put together different stakeholders that sometimes need to interact with each other. And these are very diverse, because some of these are like many of us here in this room, you know, practitioners, experts, scientists, people that really know about the data. But then there are others that are decision makers, and they're very important because they do take the decisions. But they need to have some solid base based on which they can make these decisions. And they don't have really the grasp of the scientific meaningfulness of the data. So they need to have some device to really understand what's going on. And then there is the general public, the media, the education community. So a lot of different community. We're all speaking about similar things, but maybe with different languages. So this is quite interesting because it's a bit of fun. Is what we call the hard fun, the serious fun. So where we are trying to use technology and devices from the gaming industry to make these things interesting. And let's see if we can make it. Okay, so the background is, of course, we are talking about Destination Earth. I think all this session is about it. And this is a project which is sponsored by ECMWF as part of the overall envelope. Generally speaking, the Destination Earth project managed by ECMWF are different kinds. There are the digital twin engines that I'm sure all of you know on the climate change adaptation and weather extremes. They produce massive amounts of data. Then there are the use cases application, which are very important because our customization, vertical customization of this data to try and understand how the impact is on the cities and on the environment, on flooding, on extreme event, and all of that. And then there is immersive visualization, which is what this project is about. I am running CGI Italy. I have the pleasure to share in this project my work with Privia, which is the prime contractor, and then there is also MEO and CMCC that are complementing the team. I think I spoke about that already, so this slide is just complementing what I just said with some nice pictures. One of the things which I didn't say, but I think is very important, is also to have a common playground where also scientists and practitioners that speak the same language but are focusing on different projects can interact. What we are trying to do in this project is also to bring EUMETSAT, ECMWF, and DISA more closely together and put their data together into a tool where they can see how these different data interact and create simulation and analytics. And then we need engagement of the shareholders, or the stakeholders, sorry. As I said, multiple types of stakeholders. And the way we are trying to make this more live, more attractive, more interesting for everybody is to use the gaming industry devices. So basically, our project allows the people to walk through the data using helmets, using HoloLens, all these sort of devices, by which you can really feel like you are in the middle of a hurricane and stuff like that. It will be difficult for me to give this feeling today because, of course, I'm going to show a video on the screen. But next week, there is going to be a presentation in Bonn at the second user exchange for Destination Earth, where together with my colleagues from ISPIRIVA and other colleagues, we will have a live demo, so people can go there and wear the helmet and see this data. We all know that there is an issue of scale. So this data is not only huge, not only very complex, but there is a lot of variety, different type of data and different type of skills. Okay? Sometimes we want to look at phenomena at a global level, sometimes we want to look at phenomena at a very local level, for instance, for managing cities. One of the challenges that I will talk about is to try and make this performant, fluid, efficient. And actually, these are the challenges. I spoke about some of them already, and in this picture you can see an example of a typical stereotype of a scientist and the media people. We want to create a tool which can work for all of them. Flexibility is important because we need to deal with very different type of data, but also the data has to be accurate. One of the challenges that we face in the very beginning of the project is talking to scientists, and they said, this is all very nice, but we like to have 2D traditional representation because these are very accurate. We are used to work with that, and we want to have the last digit of accuracy of our data. But we can deliver the same. We can deliver the same even in the virtual reality representation. So it's not just a simulation of a game of the things. We are using the gaming techniques, but the actual data, if you inspect the data, if you click on the data using whatever device, the mouse or your glasses or whatever, the value are the real value, okay? And then, of course, we spoke about attractiveness and performance, which is also an important issue. In order to improve the performance, we put together a data processing pipeline, which I'm not going to describe in detail, but of course, if you have a lot of questions or if you have any curiosity, you can ask your question after, visit our booth, the CGI booth, which is in the exhibition, and I'll be very happy to explain all of these things to you. In the processing pipeline, basically what we do is we have sourcing of the data using some APIs provided by ACNWF and the other tools of the Destination Earth. And sometimes we do a caching of the data in order to prepare the data and make the data suitable for visualization so that it can be more performant. And then there are some visualization examples. I have some static examples. But then I also have a video. So I will briefly present these static examples, and then I will show you a video which is probably going to be a little bit more attractive. We are presenting, for instance, wave height in different means for showing the Medicane. The Medicane is I learned this in this project, is a hurricane. We're used to use the hurricane, but hurricane normally what happens in America, and when it happens on the Mediterranean, we use this neologism, this new word, because this thing didn't exist before, and this is yet again one sign of the climate that is changing. So now we have hurricane-like things happening in the Mediterranean, and this is an event which happened near Greece, where we are showing some of this data. Here we are going to have some other visualization examples. I'm going to briefly explain them during the video that I hope will start. Okay, so again, this is the Medicane representation. This is a show. So basically, is the data that is time tagged. And so in this time series of the data, which are produced by the digital twin engines, we grab the data are moving in time, but while the data are played back in time, and you can stop, accelerate, go back and forth in your simulation, you can also move virtually across the data. So you can move the viewpoint by moving your mouse in case you are on top of a computer, or by using any device if you are in a virtual reality environment. In this case, we are showing volumetric data, which are representing the humidity, alongside a wave height, which is exaggerated. Of course, you can put as many data as you want together. After a certain amount of data, it will become a little bit cluttered. But the interesting thing is that we try to grab all these phenomena and to show them in a way that they can be useful, as I said in the beginning, for different communities, for the scientists, for the media, and to really give an impressive visualization of what is, in this case, this is the wind, for instance. No? But the wind is represented in 3D because it's 3D plus time, so eventually it's 4D. okay? And then, yes, this is quite an interesting one. This is about energy, and this is about renewable energy. In this case, we are representing with this sort of small histogram the demand and the supply of data at some point. These are, again, data that are produced by the digital twin engines, and these are real data produced by them, which we grab and we display. Along this dashed line, you see the transmission of the energy from one point to another. And then you can superimpose any other data on top of each other, like, for instance, the wind, the solar radiation, okay? This type of simulation can be useful for different things. You can use them for planning, because you can plan to establish a new, it's like geomarketing. When you want to open a new shop, where would you open it? Would you open in a place where you have more customer, where you have more demand and supply? And this is the same concept. So basically, if you want to establish or to plan a new plant, you look at time series of climatic data, you look at solar radiation, wind, all of these things, and you can understand where to better position yourself. Also in terms of exchange of energy with your peers, because you might want to be in a situation where you can sell your energy and have a business out of it. I think that's the end of my presentation, so thanks very much for your attention.
Thank you for your presentation about these visualization topics. Are there questions in the audience available? There's one.
Hi, thanks very much for the presentation. I have a quick question. I've been working on a few projects when the VR thing is kind of started. And back then we had problems that a significant percentage of our users, when they were working with it for a prolonged time, got nauseated. Did you still experience problems with that or with the new devices, or is this now a solved problem?
You mean technological problems, or?
No, when they were interacting with, well, there was one, we had a simulation game, and we also had the data visualization. They would become nauseated after some time. So they had to put down the helmet and rest for a couple minutes at least.
Yeah. Okay, so one thing I didn't mention is that we are using, well, I sort of hinted to it, we are using gaming engine, rendering engine, which are very powerful. And as you can imagine, the gaming industry is one of the more healthy business nowadays. So they're really investing a huge amount of money. No, we don't have this problem anymore. I mean, there are two issues. One is the data sourcing, okay? And this is an issue that we from Earth observation community face all the time, no? So there is a lot about intelligent caching, not duplicating too much data, but caching the data when you need, subsampling the data, using the right resolution. This is one thing. The other thing is the technology, which nowadays is no longer a bottleneck.
Thank you.
There's another question around over there.
Thanks for this very nice presentation. I was wondering a little bit, one problem that we often...
Sorry, what?
Can you hear me, or yeah? Okay.
I can, but...
Okay, I was wondering a little bit about the volume of data that you can have dynamically in when you do these visualizations, because one of the problems that we have with the EO data, with the high resolution, these are quite large volumes, and the challenges I've seen in all these dynamic visualizations is to really deal with large data cubes that go into the giga to terabyte order and how to visualize them dynamically. With the climate data, it's mostly easier because they're coarser resolution, so you can more easily deal with this. But how do you deal with this challenge, the volume of data, and how much can you handle right now?
Yeah, I mean, as much as your bandwidth allows, that's the short answer. But in terms of concept, there are two elements that are worth describing. One is the multi-resolution and the level of caching that we use. Now, I don't remember how many caching levels there are, but for sure there are at least 3 types of cache. One is when we do the data sourcing, one is when we do the data preparation, and another one is managed by the rendering engine itself. Okay, so it's all about learning how to set the parameters of these caching things to be able to render a fluid visualization. So in the end, of course, I mean, if you have massive amount of data streaming, then the bottleneck becomes the network. which is normally something which we don't control. Because of that, we have introduced, there wasn't time to describe this one, but we have introduced the concept of a show. Basically, before having a display like that, there is a user which is typically an expert user who is like a director of a movie. He prepares a movie. So he grabs all the data, visualizes all the data in reduced resolution, puts them all together, like the case of the hurricane. And once he likes the data, there is an opportunity to click on a button and to grab all the data and to cache them locally. And maybe this is going to be, I don't know, 1 terabyte of data. It's not a lot. But you cannot do this in real time. So the bottleneck is the network. But if you prepare the data in advance, then there is no issue.
Okay, I think we need to stop now. Also, many thanks for the questions and also the detailed answers. So thanks again, and we move on.
So I ask the next presenter to come to the stage. We have now Marco Corsi from EGIOS, Italy, with the next presentation. Please go ahead.
Okay. I'm very happy to be here to present this new concept. Okay, this is an error in the title, but it's basically a digital assistant for satellite data archives. We are part of a consortium. We are taking the role of an industrial partner, which is designing the digital assistant behavior and the API especially, and trying to demonstrate the usefulness of this kind of concept. And we have 2 scientific partners, which are National University of Athens and Technische Universität Berlin, which are working more on the scientific part, so models and deep learning models, especially, and knowledge base and natural language processing, because these projects try to bring together this kind of technologies. So why digital assistant? Well, we are in a world where archives are really different. There are a lot of different data. And for example, in the destination Earth, there will be a lot of different data coming from different topics. And the other point is that, well, we are in the year of ChatGPT probably. It's the major innovation in the world of digital product. And I think that in a way, we will, it's inevitable that these natural language interfaces will take over and will be more and more used by also by developers, by common users. Basically, a digital assistant is a chatbot that can be used to ask questions, and ChatGPT is an example of a general knowledge digital assistant. What we wanted to do is to provide a different model. So we have a demonstration phase, and we start selecting use cases. One is organized with 2 data sets, basically vessel detection, so a data set that is based on dynamic changing features on the images of vessels, and water bodies, which are more fixed features on the images and does not require and can be suitable also for used with different images and different sources of images. So, for example of what we would like to address is allow users to interact with our system, especially with the API, and for example, show me all images with rivers in Emilia-Romagna region. Or, and this is a classical text query that is going to be asked to a catalog in the end, but you have to recognize named entity like Emilia-Romagna, and also the fact that you are looking for rivers and so on. Then there is other example of this. You can read it if you want. Basically, another example, it's a more direct questions or requests to the system to find, to locate features in images, in patches of images, so you can upload in images and ask if there is, for example, water bodies in the images, and this is more directly the use case that we are addressing right now. Another possible use of this kind of technology is to construct data sets, or just to address patches of data set in a deep learning model that are not really, that you are not happy about. So if you, for example, if you're training a model, you obtain not very good results in, for some kind of patches, you can ask to the engine to provide similar patches like that, and you can verify if there is some pattern in this kind of errors, in this kind of classification errors. So this is another possible use of this technology. So we will also develop a prototype UE for obtaining feedbacks on the technology. So basically, we will have a map interface and then interaction using a chat interface, and we will obtain data on the basis of the questions that we have seen before, and then we will have specific tools to address different tasks, such image similarity or something like that. So the point is to also to understand the feasibility of the solution at large scale, because of course for the generation of the data we need a lot of processing power to just construct the data structure that are needed for image retrieval, for analysis of the images, and also of course there is the training part that is also very important. So let's come to the more scientific part, so the engines that allows us to build the demonstrator. So basically two sections. One is the one that is related to text analysis and linking with semantic knowledge. In this case, it's based on EarthQA and is developed by National University of Athens, and is an engine that basically takes text questions, and analyze the question, extract name and entity, and construct a GeoSparkle query that can be sent to a database which contains different entities and that are linked in RDF structure. So basically, for example, we put metadata and the features from databases. This is more or less how it works, and it uses, for example, in the where, in recognition of a where clause and in the recognition of ask select statement, the uses language model, large language model like Llama 2, but basically this is more or less the workflow that is using. And of course, in this work, we used a benchmark dataset. It's the GeoQuestion dataset, and you can have a look at it and use it and help improve the dataset too. Then let's come to the image-based engines, computer vision query engines. Basically, these are based on, they are looking to provide capabilities to extract, retrieve image. In this case, can be unimodal. Let's say you send an image and you obtain similar image from the engine, and cross-modal, so you send the image and caption, and image or caption, and you obtain the same result. So images that are similar, and of course, depending on the caption that you send, for example, forest, you obtain images that contain a forest. These are based on two different models that does the same thing. So basically, these two are more technical details on the models that are based on two different techniques, but basically the final output of the models is an hash that can be used to scale the fact that you are searching images over large amount of data. So this is more or less the concept of these models that are used basically for image retrievals or content retrievals from big data stores. And of course, as part of the project, there is improvement to open source libraries like this one, which is able to connect to different words like computer vision. So the team library is very famous for computer vision tasks. And Hugging Face, which is most known for language models. And you can connect and you can test it in a way. And then coming to the data sets, there is the possibility to use the previous library, of course, with this kind of data set, which is already providing what you need to perform visual question answering on images. So these are some examples. Well, thank you.
Thank you, Marco. So we have time for question. Anyone a question to Marco? If not, then I have a question for you, Marco. What were the sort of biggest challenges that you encountered, and how do you think, what is about the option to put this into production?
Yes, one of the biggest challenge for sure is to integrate the different models into a user interface concept or API. On the API, it's easier to provide single capabilities, but on a user interface, it's very difficult because, of course, we are used to develop like catalog interfaces that are classical with selection and search box and so on, and a lot of features. In this case, you are just providing a user interface, which is a chat, and then the user can interact. And of course, particularly on this topic, there is the problem that after 1 year of ChatGPT, people expect like that the chatbot it's answering to everything. And it's not easy to match the performance of such model, of such systems, I would say. It's not only the model, because the model are very good right now, the language model, but the systems are very difficult to match. So OpenAI has a very big architecture on that. So this is the challenge for us. To put in production this kind of system, and the risk is that at the end, we will go to OpenAI because, of course, it's very difficult to invest in such a technology. That.
Thank you very much, Marco. Okay, one more question I saw, Vasily.
Hello, I'm from IMMERSIVE. I'm familiar for both the work from University of Athens and from University of Berlin. So how you envisage that this can be used in the context of DESTINE? Do you believe that there's a use case for that, or is it something that can be adapted, can be used there?
Yeah, I think that every data archive that has a lot of different data, but not all the data, also models, can be a very good landing spot for such tools. And in that case, I think that the approach based on a knowledge graph, it's also a better approach because it's more like it is not providing answers that are wrong. It's based on knowledge, on real knowledge, so it's providing like links that are effectively there. So providing such capabilities to interact Of course, we probably have to improve the part of natural language interactions, but as also Nino said, it's important to provide interfaces that are easy to be understood by decision makers. And of course, they are expecting to not to use Jupyter Lab or anything like that. If they can really do the work using a natural language like a chat, I think it could be very useful. So,
thank you, Marco.
So thank you, and we come in our agenda to the last talk of the session. It's focusing on 3D radiative digital twins to support EO, big data generation. And the talk is given by Yves. He's founder of Reference, SME providing expertise in radiative transfer modeling. So with this, Yves, I hand over the floor to you. Please start your presentation.
Thanks a lot. So it's a pleasure for me to be here and to give this presentation on behalf also of my co-author, who are from University of Lancaster in UK, sorry, and with the Grasse company in France. So the first question I would like to answer is why to introduce this concept of a radiative digital twin Earth. And to give a bit of context to this, I would like to take an example from the numerical weather prediction community, so those who are doing the weather forecast. Essentially, what they are doing is collecting a huge amount of observation from ground observation, but also from satellite data. And all these data are used to feed a model, a mathematical model, which essentially solves the Navier-Stokes equations, and through an assimilation process, provide all these data on a regular grid, a three-dimensional grid, so in space. And then from there, you can do a forecast at a regular time interval. And so actually, these data sets are of very high quality because they appear on a very regular grid, unlike the observation. And thanks to these features, so these big data sets have been used successfully to train AI-based algorithms and to provide accurate weather forecasts. So then you might say, okay, it's a done deal. We don't need all these models. We can do no directly weather forecast with AI. Actually, not quite, because so they are based already on assimilated data, and they could have trained the model based on observation. And so let's focus a bit on what's going on here. So concerning the observation, you have ground observation that directly observe variables like temperature, pressure that are provided to the model. You also have a lot of satellite data that can be, through retrieval algorithm, converted into a geophysical variable of interest like temperature profile, or also radiance can be directly assimilated. But what we have is a zoo of different data, and so those who have trained AI to do weather forecast, they choose not to use these data because they are too complex to use. Now, there are some cases where radiance are directly assimilated into the model. In that case, at ECMWF, they are using a fast 1D radiative transfer model called RTTOF, but it assumes that the Earth is flat, that the surface is uniform, and that the atmosphere is planned parallel. So it's quite crude assumptions. So what we propose here, in order to be able to use space data to train AI, is actually to simulate a very large number of satellite data using the irradiate model. So the irradiate model is an open source 3D radiative transfer model, which is designed to simulate satellite observation, but also in situ observation. That's a very interesting feature. It includes a very high quality atmospheric model. It allows a detailed representation of the surface. It accounts for the sphericity of the Earth. and the radiative transfer equation is solved with Monte Carlo ray tracing. So the development of this model is funded by ESA through Copernicus Calval Monet. So it's really designed to support Calval activities. It comes with a very nice Python interface. It is provided with a very detailed documentation, and it's a free software. So here you can see the web page where you can have access to this code. It's on GitHub, and it's for free. So with these, our idea is to be able, or what we propose is to simulate a very consistent and nice data set. And to do what? So the idea is to propose a digital representation of the Earth as seen from space or ground-based observation at various spatial scale and also temporal sampling. And these should really help to bridge the gap between observation, so satellite observation and ground observation and machine learning algorithm. So how to generate these big data from these radiative digital twin Earth? So first we have to look at what are typically the quality of these big data. So for some of you who are familiar with big data, you know what it is, but these aspects are often overlooked. And so first what we want to have is the reliability of the data. So in this case, we want to simulate satellite data, and we want to be sure that we indeed, we can trust the data and we account for all the features of the data we want to simulate. We also, and that's critical, want that these data are unbiased, because otherwise you won't be able to use them for the training. And the last element, which is extremely important, is the representation of the features. And in this specific case here, we have to make sure that the key radiative processes are correctly taken into account. And so I will really focus on these aspects in the rest of my presentation. So in order to simulate this satellite data, we intend to collect, or we propose to collect data from the Copernicus service, and most of these data are really state-of-the-art and of very high quality, and also some ancillary data like a digital terrain model. That's at the global scale, but also at the local scale, we intend to generate extremely detailed scene where every single leaf is represented. And so it's important that these data, of course, are input data of high quality and unbiased. And then passing through a scene generator that will describe this scene in a way that can be understood by the radiative transfer model. And that's where really we make sure that all the physical processes that we want to describe are taken into account. And the idea is to be able to simulate various satellite data at various spectral and spatial scale, like up to MODIS with a resolution of 250 meters, up to a drone with a resolution of a few centimeters. Now, it's very important to be able to demonstrate that we are able to accurately simulate satellite data. And for instance, in the case of simulation of a bright desert, which is often used for vicarious radiometric calibration, we are already capable of simulating satellite data with an accuracy of about 2 to 3%. Okay, now in order to illustrate the importance of representing correctly features, so in that case radiative transfer process in the big data, I've chosen a very simple case study over the Sahel region. So the Sahel region is located here at the south of the Sahara Desert. It has 2 seasons, a dry season and a wet season, and it's a quite fragile area in terms of climate. So last centuries, during the 70s and the 80s, it has been subject to quite important climate perturbation. So in terms of land cover type, so from north to south, it goes from open grassland to degraded evergreen forest. And so here you have an example, for instance, of so-called open deciduous woodland or savanna. And during the dry season, so this region is subject to intense fire because you have this grassland here that can burn very easily. And so it has two consequences. First, the reflectance of the surface will change quite drastically. And secondly, it will emit in the atmosphere a quite important amount of smoke. And so if you look at time series of satellite data over that regions, either of surface reflectance of aerosol, often you see a zoo of different results. And this is due to the complexity of the process that I would like to illustrate now. So in order to do that, we have reconstruct a virtual savanna, where you can see here is this grassland, the trees. In that case here, we haven't yet put an atmosphere, and you see that as on the moon, the shadows are very black. Then we put an atmosphere on top of it, and you see that while the scene is exactly the same, it will appear quite differently. The shadows are much smoother. And finally, we put a layer of smoke here, and you see how the perception of the scene changed. This is due to this coupling between the surface and the atmosphere. So now what we would like to do is to see these three scenes as seen from space. And here you have an example of how these scenes appear. In the case there is no atmosphere, it's just to illustrate. So here you see the background and then the trees and the shadows of the trees. And so what we have done is simulate these from space in the case of no atmosphere, clear atmosphere, and this biomass burning. And to be more realistic, we have simulated MSI data, so Sentinel-2 with a resolution of 10 meters. And in order now to understand how to do this information content analysis, we have here given a very simple example where we have changed the illumination angle from 60 degrees to 30 degrees, and you see the impact already on the image. And we look at these in the blue and in the red spectral region within this RGB image. And we simply look at the difference. And you see, for instance, in the blue, the impact is to increase the signal. And in the red is to decrease it. So it's really
Excuse me, we need to close soon.
Yeah. So then what we will do, what we have explored also is the possibility to represent this big data representing separately the surface and the atmosphere, so the surface without atmosphere and the atmosphere with a black surface, and to see whether we can reconstruct the image this way. And so what we observed, so we look in the blue spectral region, you see that here, when there is no atmosphere, the surface is quite dark. And when the surface is here, there is no atmosphere, no surface. We see that at the end, most of the signal comes from the atmosphere, while in the red spectral region is the opposite. Over a dark black surface, the signal is very dark, and when there is no atmosphere, most of the signal here. And so what we will see in the next slide, and that will be the last slide before the conclusion, is so we will compare these images here, which is simulated with all the processes, with this combined, this fusion, linear fusion of the contribution from the surface and the contribution from the atmosphere. And we see the difference between the two. And if we look in the blue region, we see that on the average, it's quite good. We have a difference of about plus or minus 5%. But if we look in the red spectral region, we have difference up to plus or minus 20%. So what does it mean? So you can build your big data, summing these two contributions. You will have an image, but the problem is that the physics in this image will be wrong, and it will be very difficult to train your data. And so these are my concluding remarks. So as I'm a bit late, I suggest that you read these remarks while I'm taking the questions.
Thank you. Yeah, thank you for your talk. Unfortunately, we really consumed the whole slot and we can't allow questions for the moment. So please come back to the presenter after the session in order to ask your questions. Yeah, so with this, we conclude the whole session. I thank all the speakers. I thank all those who asked questions and contributed. So with this, we close the session and hand over actually to Peter Campanius for the follow-up session. Thanks a lot.